Hello physics students, Mr. Thrasher here again. This video is kind of us wrapping up the basic ideas behind light. Now there's quite a few little subtopics in this video, but I'm going to go quick, and that's tough. One, light is probably my favorite subject in all of physics. Me being an astrophysics and astronomy major, everything I learned about it was based upon light. But I want to go quick because one, I want to, again, kind of meet our 10-minute cap for these videos. Also, quite a bit of this should have been review when you were back in middle school. If some of this is brand new, of course, you can hit pause or you can go back and rewatch things. But I'm going to go quick on certain sections. Okay, so let's continue on. Here I have my agenda. Hopefully you found this meme kind of funny after our last video, huh? All right, if you don't remember, we have our guiding question, of course, for this unit. And as we come back from spring break, let's remind ourselves we're trying to understand the physics of sending and viewing a snap, or like an Instagram post. Okay, we're gonna get into some technology aspects about phones a little later. But if you don't know, there's a lot that involves light when it comes to viewing and sending things on your smartphone. So we gotta spend time understanding light and other types of light besides just visible light. So first part, different terms, different words, different vocabulary that's associated with light. Unfortunately, over the decades and the centuries, scientists and philosophers have used different words and different terms to describe light, but they're all referring essentially to the same thing. The first, and probably the most common one that I say, is a light wave. Light is a wave, or at least it's partly a wave, or it acts like a wave. Okay, and so here's a basic diagram of light acting like a wave. It acts like a transverse wave. Okay, light is not a longitudinal wave, it's transverse, so the easy one to draw, up and down, up and down. Okay, light wave. To be honest, another term is often employed, especially when scientists or engineers or whoever wants to make diagrams to understand how light is traveling, and that term is light ray. If you remember the term like X-rays, right, there's that word ray. Often scientists will, instead of drawing a wave, which isn't too bad, but I mean that could get a little complicated or confusing if you're drawing a lot of waves in a given area. So instead, a scientist will just draw, or someone diagramming will just make an arrow. This is representing a transverse wave of light. So imagine like the ups and downs and ups and downs and ups and downs, or like that. So if you see a diagram and it has just these arrows labeled as waves or light, don't think like there's something weird going on. It's just a simplification for making that image. Okay. Also, after the last video, you should be clear in that light, it definitely acts as a wave, but it also exhibits particle properties. And so there's another term, photon. I believe Einstein came up with that term. I might actually be wrong, but certainly this term photon has been used a lot after this wave-particle duality thing. Okay, and I like this diagram a lot because it kind of shows both. Remember, particles, think of like little BBs or little balls. So this classic diagram, sometimes called a wave packet. Here you see the wave property of the light. And also it's kind of like composed in like a little, almost like oblong, like a little football. Here's the particle part of it. So you might see a diagram like this. Also sometimes, and there's some simulators we'll see, they'll say it's a light photon. They'll say that the flashlight is shining photons, and you'll just see them as little balls. Okay, they're just showing the particle kind of side of the light. So don't get confused. Because again, you know, light's difficult. It has these multiple properties that are different than how we're used to looking at things. But those are three terms. There's another term, electromagnetic radiation. Fun to say, really fun to work into a conversation. Like if you want like your parents or something to turn down the lights and say, oh my gosh, turn down that electromagnetic radiation. They're gonna look at you and think you're super smart. That is also just light, electromagnetic radiation, fancy term for light. Radiation coming from atoms, remember from our last unit, and light is created from atoms, and we'll get into those details a little more later. So we have these different terms for light. We're still kind of working out what light is. We know it has wave properties, particle properties. If we focus on the wave properties of light, we know waves are traveling through something, or at least they cause a disturbance in something. Like sound waves cause a disturbance in air particles, or I mean, it could be liquid, right? You could hear things underwater. Ocean waves are disturbing water, ocean. But what are light waves disturbing? And maybe you learned that light doesn't need a medium to travel through, right? Light can travel in outer space, and that's true, but that doesn't mean that it doesn't cause a disturbance of some kind. So what is light a disturbance of? Maybe you didn't learn this before. I'm going to bring you back to this word we saw in the last video, electromagnetic radiation. The key, and our almost throwback Thursday, if you're watching this on a Thursday, is from this term. What are light waves? They are electromagnetic. Electro referring to electric, and magnetic, of course, referring to magnetic. So light is composed of some quality of electric, think electricity, and some quality of magnets. How are electricity and magnets related? Oh my gosh. Do you remember way back when we had this adorable little piece of paper? Way back when I could actually hand you papers and you could put them in your binder? We use this to both discuss how electricity and magnetism are related. We did that in our power plant unit for generators. We saw this again to understand how wireless chargers are able to power your phone. This relationship is also what creates light. If we skip some of the finer details, if I can create an electric field, well, when you create an electric field, that creates a magnetic field. And what happens when you create a magnetic field? You create an electric field. That's what light is. In fact, these three units are actually all very much tied together almost by this single little page of notes that we have. Light is oscillating. It's changing electric and magnetic fields. Here I have a picture and a visual. Okay, light's a little more complicated. Technically, you really shouldn't be thinking of it as just one transverse wave. There's really two in a given wave of light. There's an electric field, and that creates a magnetic field. So they have it here in red and blue, and they end up being perpendicular to one another, though we're not going to get into why. Okay, so electric fields create magnetic fields, they create electric fields, and that process repeats. That's why you can have light in outer space. You don't need any kind of medium. These are self-replicating, so to speak. They're self-producing. So I like this GIF, this diagram right here. What direction would you say the wave is traveling in right here? Yeah, it's kind of going this way, right? Yeah, again, the electric and magnetic fields are oscillating perpendicular because that's what transverse waves do, but it looks like the light wave is moving like this. If you kind of unfocus your eyes, it looks like it's kind of going like that. So when you are seeing the color red, you are seeing a certain fluctuation of electric and magnetic field lines entering your eye. This is really weird and really unintuitive, right? All right, but that's what light is. It's composed of oscillating electric and magnetic fields. Okay, we're going to pick up the pace a little bit right here because, again, a lot of this should be review. When we talk about visible light, we're talking about the colors of the rainbow. That term will be used a lot, the rainbow, right? This red, orange, yellow, green, blue, violet. I don't have indigo in here. I don't have Roy G. Biv. I have Roy G. Bv. If you're interested to understand why I don't have indigo, which is a color we're frankly going to ignore in this class, as most scientists do, I have a couple optional videos in the description. You don't have to watch them, but if you're interested in learning some more like why we don't have indigo in this, go ahead and watch those. But classically, visible light, the light that we can see, it's a spectrum. Spectrum just means range. Here's the range of different colors. We have red and we have purple. Okay, the only difference between these types of light is how big or small their wavelengths are. And of course, how big and small their frequencies are. So red, this side here, this has the largest size waves or the smallest frequencies. Violet has the smallest wavelength or the highest frequencies. So here's a diagram of the wave, and notice the wavelengths are changing and they correspond to these different types of light. And here I have it as a photon, right? Blue has a higher frequency than red, okay, and red has a larger wavelength. What do you think this would be? Oh, this is actually not black. Black is not a type of light. This would be representing like infrared light, but we can kind of ignore that. So the visible light spectrum, it's the colors of the rainbow. Okay, white light is a combination of all the colors of the rainbow. I have all with a little asterisk because you're going to do an activity where, you don't necessarily need all the colors of the rainbow because that's not necessarily what your phone uses, but I'm not going to get too much into that because that's part of your activity. But there is no single wave of white light. There's also no single wave of pink light. or brown light. Huh, I wonder where those colors come from. Okay, and as I mentioned before, the electromagnetic spectrum as a whole is much bigger than visible light. Here's visible light, but all the other things, radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, they're all the same thing. They are all those oscillating electric and magnetic fields. The only difference really is their size. Radio waves are huge. They can scale from the size of houses to soccer fields to mountains. We can't see radio waves, but if we could, they're gigantic. And there's radio waves passing through you all the time. Wi-Fi and 4G LTE, that's using radio waves. Microwaves are a little smaller. Infrared's a little smaller still. Gamma rays, which we've learned about, are some of the smallest and some of the highest energy. So over here we have small waves, high energy. Over here we have big waves, low energy. All right, and visible light, this is just the tiny little fraction that our eyes are sensitive to. But there's all these other types that exist. We should hopefully know already a little bit about reflection and absorption. Light can reflect off material. You see something as green outside when there's sunlight, and sunlight has all the colors of the rainbow because all the colors of the light are absorbed except for green light. You see light when it enters your eyes, and if you're seeing something green, that's because green light is entering your eyes. If you're seeing something as red, it's because red light is entering your eyes. My car is white. I see white because all the colors are bouncing off. You see something as black because none of the light is reflecting. Black is an absence of light. It's like a void. Think of like black hole. You see something as black, or things become darker and darker when there's less and less light entering your eyes. And then like glass, well, that's letting the light go straight through. It's not really being absorbed or reflected. It's just passing through almost as if it wasn't even there. Okay? Last thing I want to talk about, okay, because I think it's super interesting. I know I'm at 12 minutes. I'm going to go for a couple minutes longer. If we think of reflection and mirrors, I love this topic because mirrors are really your brain not understanding what's happening. And here's what I mean. Okay, your brain forms an image based on how the light enters it. Okay, you see your microwave over here because light from the microwave is entering your eyes, and your brain and your eyes detect that light. It also kind of like detects the direction, and your brain assumes that light travels in a straight line. And that's a very good assumption. Okay, if you see your computer screen right in front of you and then you closed your eyes and you felt around, you would feel your computer screen because the light from your computer is traveling in a straight line into your eyes. Your brain is always assuming light travels in a straight line. And that's almost always true, except in mirrors. Because in a mirror, light from your shoe, this ray of light normally wouldn't enter your eyes, right? It's going up and to the right. But if it hits a mirror, it bounces off. And now that ray of light, those waves, are going this way. They enter your eye. Your brain's like, oh, I got light. Your brain always assumes that light travels in a straight line. Your brain does not know that it bounced off of a mirror. So your brain assumes the light came from somewhere over here. So it forms that image of brown leather on your shoes as right here. And the top of your head, the light comes in and it bounces off. Your brain doesn't know that light bounced off, so it thinks and it forms that image over here. Your reflection in a mirror is frankly your brain not understanding what's going on. Okay, I'm going to cut my video off right there. I have some additional videos about color and light and our perception of light, again, in the comment section, in the description setting. They're optional, but if you're interested in light like I am, I think they're good videos to watch there. They're pretty interesting. Okay, but I'm going to stop there. Thanks for watching.